Alright, so the semester 1 review video, as requested by some of you, we will start with significant figures. So the 4 rules of significant figures. 1, all non-zero digits are significant. Alright, so anything or any numbers 1 through 9 should be considered significant. So you look at the examples to the left. 543. Well, 3 significant figures. We have 1, 2, 3. Right? Keep going. 22.437. Okay, we have 5. Alright, 1.321754 has 7 significant figures. Rule 2. All zeros between non-zero digits are significant. Alright, so if we have bracketed zeros, alright, so has 3 significant figures. Okay, then we're going to have 1, 2, 3, 4, 5 significant figures here. Alright, now we go to rule 3. All beginning zeros are not significant. So once again, you can see the examples here. Okay, lots and lots of different zeros. Okay, just know right here, 1, 2. We have 1 right here in 0.02. Now, here's the tricky one. Refer to rule 2. Coming down to this, we have 3 and 3, and the zeros bracketed by those numbers are significant as well. So we don't just have 2, we have 4. Right? Now, rule number 4. Ending zeros are significant if the decimal point is actually written, but is not significant if the decimal point is an understood decimal. Alright, so we look right here. Okay, why is this 5? Decimal point is written. 1, 2, 3, 4, 5. Alright, 7 significant figures. 3. Now here's where we get into these bottom 3 are implied. Okay, they are understood that the decimal is somewhere in this number. So we go to 100. It only has 1 significant figure. Okay, there is an implied, an understood decimal point at the end of that 100, but it is not written. Okay, 302,000 only has 3. Once again, that zero is bracketed. 1, 2, 3. All right, but do not count those zeros. All right, last but not least, we have 1 bracketed 0 is 2, 5 is 3, and this little 0 here, don't worry about him. Only have 3 significant figures. Okay, so let's talk about a couple of different models. We have Dalton. If you remember, Dalton said, well, there were tiny little solid particles, all right, the atom, and they made up everything. So we have water, which today we know has 2 hydrogens and 1 oxygen. But what Dalton thought was, no, this wasn't 2 hydrogens bound by oxygen. Okay, he thought, well, we have 1 little tiny atom, and that was a water atom. Okay, and he also said, well, maybe we have methane. Well, methane was its own little tiny atom. Let me make that a different color. That was a methane atom. Everything in the world was made up of its own little solid atom. It had its own. Okay, so wood was wood, metal was metal. Didn't matter which metal. If there were different types of metal, say iron versus steel, there was an iron atom and there was a steel atom. All right, and these did not combine. Right, so your feet would be made up of feet atoms, human atoms. Okay. Then we moved on to Thomson. And Thomson had that plum pudding model where he thought, yes, there's an atom, but there's not just a tiny solid ball. This was the plum pudding model, or chocolate chip cookie. Right? So there were protons floating around in this plum pudding, since none of us in any of the classes have had plum pudding. Well, we go with the chocolate chip cookie ball. Mashed together, there's chocolate chips. Inside there, those are the protons. They're floating around in this atom, but that's all. Okay, so there were protons in this cloud or sphere that made up the atom. And then Rutherford's experiment. Right, we talk about Rutherford, and he was the one who shot at a gold foil. I don't really have gold on here, so we'll do our best. Shot gold foil, and what happened was this light did not just go straight through, but in fact it went crazy in all different directions, and in fact bounced back. And that was the discovery of the neutron. Alright? So finally, once lots of years went by, we now have our protons and neutrons in the nucleus, right? We got our P plus, our neutron, and then we have our orbiting electrons. Alright. Okay, so let's take a quick look at the difference between filtration, distillation, and electrolysis. Okay, so filtration, we're going to start right here, diagram 1. So we have a beaker full of a heterogeneous mixture right here. Remember, heterogeneous, we can tell the difference. That's like a pepperoni pizza. We can tell the difference between the crust, the cheese, and the pepperoni. A salad, okay? It's mixed together. We've got carrots, depending on the salad you want. We've also have fruit in there. We've got dressing, etc. Where a homogeneous is we cannot see the particles. Okay, salt water, it is dissolved. Okay, so filtration is dealing with a heterogeneous mixture. All right, so we can see the heterogeneous mixture is poured into the filter paper. If you remember way back when we first were going over this, I said that some of you, or probably your parents who brew their own coffee, use filtration every single morning to make their coffee. Okay, so the coffee is added to water, all right, in this filter. Here's our coffee, is this green. All right, we can say also this is salt water and sand. Okay, we've taken a big bucket at the beach, we've scooped up salt water and sand. Well, to separate the sand, which is the green, right here, okay, we're pouring it through a filter paper in a funnel. Well, now we have the salt water dropping down into my beaker here, and it is salt water with zero sand. We filtered it perfectly. There's no sand left. All we are left with is salt water. Next, we move to distillation. Distillation is a little different. Inside my beaker and or test tube, right here, I am now going to set a flame. And I am going to bring this to a boil. Yes, that is a Bunsen burner. It is a horrible drawing, but that's okay. We're going to heat up this salt water. Okay, right here is the salt water. Okay, and it is going to evaporate and travel down our pipe, and only our water is going to be left in our beaker. So the salt then, okay, we've evaporated all of our homogeneous mixture. We have separated the salt, which is going to be left in our test tube, and our water, which is going to be in the beaker. Next we move to electrolysis. And finally, electrolysis, we're going to have our water, and we're going to run an electrical current through it. That's supposed to be a lightning bolt. That's horrible. Anyway, we run an electrical current through the H2O, the water, and that is going to separate the hydrogen and the oxygen ions. Right? That's simply all electrolysis is. All right. Now, the periodic table. Please remember, yes, our groups are vertical. Our rows are horizontal. Now we're primarily going to focus here on groups. Okay? And there's a reason for that. If you can remember, the groups we labeled 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Okay. We also, on our groups, have the alkali metals, the alkaline earth metals. We come over here. We have the noble gases, and 7A is the halogens. The significance right here to these noble gases are they have a full octet. And what I mean by the octet would be they have 8 electrons. Okay? 8 electrons in the outer shell. What that means is they are not going to readily seek out bonds. Either covalent or ionic, does not matter. They do not like to bond. Every single element on this periodic table is trying to have a complete octet, or 8 electrons in the outer shell. Okay, well, if we work from 1A group to 7A group, those are going to be the most commonly bonded groups. Okay, and 1A has 1 valence electron. Okay, so that has a positive 1 charge. Next we move to 2A and has a positive 2 charge. 3A, positive 3 charge. Now 4A, right here. This group is a plus or minus 4. So they can either give away 4 electrons or gain 4 electrons when bonding. They're pretty significant. Okay, they're special. Nitrogen's group, right here. Okay, this is 5A, but now we turn to 3 negative, and then 2 negative, and 1 negative is the halogen group. Okay, now those charges are what are significant, especially when we get into ionic bonding, or more recently writing formulas, balancing equations. This all plays a part. All right, so let's take a look. If, say, I ask you the charge of lithium. Lithium is 3 right here. Okay, and what do I mean by 3? Well, the atomic number, three, tells us that it has 3 protons and 3 electrons. Alright, so everything on the periodic table is neutral. Alright, it is neutral, so 3 positively charged particles, 3 negatively charged particles does lithium have. Now we look down below, and it's hard to see on this, but